We're going to talk about this simple machine learning technique, KNN classification. We have some observations that we've already classified, and the goal is to take an unclassified observation, something we don't know, and predict what classification would be best for that. It's a simple idea and an extremely simple procedure. We'll just look at its neighbors and assume the new observation will be classified the same way as the things around it. KNN is just simple notation for the kth nearest neighbor. We choose k to be an odd number because we're taking a vote at the nearest neighbors that were already classified, and an odd number avoids a tie vote. If I choose to look at the 3 nearest neighbors and 2 out of 3 are classified in a particular way, then this procedure would predict the new observation should be the same. The art comes from trying to define near. By what measure are we going to say one thing is near to some other thing? It's a perfectly simple-minded machine learning technique to implement once the background is set up. But there's a lot of complexity about how to set up that background. What exactly is near? How near is near? Suppose we want to classify somebody as whether or not they're likely to be admitted to college. Typically, college admission is going to have some weight on GPA, usually between 0 and 4. Admissions might have some weight on SAT scores between 200 and 800. Clearly, 800 is a little different from 4. They're very different scales. If we constructed an index that just added the two numbers together, then you'd basically have a classification based on SAT score. Because whether somebody got a 604 or a 601 doesn't make a big difference. Not compared to somebody else who got a 611 or 624. So going back to our previous discussion about normalizing, this would be a case where an analyst might normalize both scores to be in the 0-1 interval. Is that enough? Is there other information that's relevant? That's where the artistry comes in. Now this is a good place to take a detour. The scaling problem is very similar to questions of ranking. We see a lot of rankings out in the world, especially in the popular press. Somebody produces a ranking about the top colleges in the US or the best cities or the best athletes ever. A while ago, Sports Illustrated did a ranking of the top athletes of all time, which somehow managed to compare Babe Ruth with Serena Williams with Secretariat. Yes, the racehorse. Total clickbait. But even comparing athletes within a sport is tough if they play different positions. Now you might ask, does statistics give me some sort of guidance on how rankings ought to be done? And the answer is, in general, no. Sometimes I know it feels like a lot of what I'm teaching you is actually things that you might have hoped you'd know, but actually, no, sorry. I apologize for that. But rankings are really difficult. If we have a simple distance measure of a one-dimensional variable, then we can manage a ranking. In sports, we can rank. How many games did a team win? That's a number. It doesn't take fancy math to determine that 17 is a bigger number than 16. So we can rank 17 wins above 16 wins. What about tie games? Sorry, no good answer. Once you add even one more variable, you're looking at a two-dimensional graph, so you need to weight the two distances. With 3 numbers, 3 dimensions, all the wheels come off. As economists, actually, you should know this result. This is right out of microtheory, from Ken Arrow's impossibility theorem. Arrow demonstrated it is generically impossible to aggregate together different people's utility functions. A ranking of bundles is a sort of utility function. Thus, it's impossible generically to come up with any ranking that satisfies basic desired criteria that will accurately aggregate together the preferences of more than one person. You might hope there's some measure to do rankings the right way, but the answer is no, nothing. It's generically impossible to do. Sorry. Back to our KNN machine learning. For our example in class, we'll look at people's choices about getting their kids vaccinated against COVID. The household pulse data has extensive data on that, broken down in the age of the kids, under 5, 5 to 12, 12 to 17. I'll use data on the 12 to 17 group as an example. You can look more deeply. It's interesting how some people with multiple kids have different answers by age. These are complicated choices. We'll cut away the people who don't have kids in this age group, which is why they're coded as NA in the data. Now, typically, when statisticians estimate machine learning models, they're going to normalize all the data, and that's the first piece right here. The first few lines create a new function, normVarb. This function takes in x in, subtracts the minimum, divides by the difference between the max and the min. Every normalized value will be between 0 and 1 inclusive. In this case, I'm trying to classify decisions about vaccinated kids, so ask what variables are going to be relevant in classifying. I'll start with just people's education and the state they live in. Now, to be clear, this is not the greatest way of coding. I'm just starting with something simple, leaving plenty of room for you to do better. I'm coding both of these as numeric, which means they're going to be treated as continuous variables where the distance between the codes has some meaning. In education coding, that's maybe not terrible since the data are coded where an advanced degree is a higher number than a high school diploma. But for states, that's a pretty crap assumption. The codes are alphabetic. Alabama is close to Alaska, which is close to Arizona, while Alabama and Mississippi are far away. I'm leaving plenty of space for you to do better. I'm deliberately taking only a few classification variables because one of the other issues of geometric nearness is that as we get into higher dimensions, it gets tougher to find neighbors in a sensible way. Our human intuition does really well in three-dimensional space. It can understand forward, back, left, right, up, down. But what does five-dimensional space look like? My poor human brain doesn't know. I have no capacity to visualize that. That's true for most humans. One of the ways our human intuition can lead us astray is although we have a sense of nearness in low dimensions, that crashes in higher dimensions. Generally speaking, KNN estimators are not going to work very well if we add in too many different classification factors. But I'll ask you to play with it, see for yourself. So I put these elements into a data frame, pick up only the complete cases because this particular algorithm will choke if it has missing values. Let's talk about the plan. In many machine learning estimations, so again and again in this class, we're going to split the sample into two groups, the training group and the test group. We use the training group to train the model. Then pretend we don't know the answer for the test group and see how well the model can predict the test group. It's crucial the machine learning routine doesn't see the data in the test group. So I split the data in these two groups using 80% as training data and then 20% as the test data. See how it does. The next line of code is set seed 1, 2, 3, 4, 5. The hell is that doing? We will come upon this again regularly. The way computers work is if I tell it to pick a random number, the computer is not actually going to pick a random number. The computer is going to pick what's called a pseudo-random number, a number that looks like it could be random, but is actually determined by a rule. In computer science, people have spent a huge amount of time worrying about this. It was a major innovation to figure out how to do that. If you want to read some of the background help files about the details of pseudo-random algorithm, go ahead. It's kind of lovely. But all you really need to know is this pseudo-random procedure takes a seed value and then uses an algorithm to create a pseudo-random number. So if we give it a particular seed, then it will always pick the same random number. Maybe we don't want to call them random, they're actually pseudo-random, but we could also call them good enough random numbers. By setting the seed, if I run the exact same estimation again, I will get the same random numbers chosen, which is helpful in making your code so somebody else can run it and get the same results. If you run this on Friday and somebody in your study group does it on Saturday, you'll get the same results. So with that seed value, the next line of code is selecting 80% of the sample at random, actually at pseudo-random. The UNIF is picking random numbers from a uniform distribution between 0 and 1. It's going to be a whole long list. If the random number is less than 0.8, it returns a value of true. If it's greater than 0.8, then it returns a value of false. It's a way of randomly splitting the data, so 80% go in the training set, 20% into the test set. Then there's some lines that give a summary of the data that we're using, mostly so you can check that it looks okay. Where not okay would be like if there are lots of missing observations or the numbers are not between 0 and 1. Then this is the actual meat of the KNN estimator. I'm putting it inside a loop where the loop fixes the number of neighbors to be used from just 1 neighbor, then 3 neighbors, then 5, up to 9. Odd numbers, so there's never a tie vote. Each time it produces a set of estimates. Each time checks how well those estimates did in predicting new data, the test set. How often does it get the right prediction? In the lab and class, you can mess around to try to improve on this very simple model. Have fun.